Let's sort of roll forward to a slightly rebuilt future. Chris, what did you do?
Yes, you destroyed everything. I want to see if we can rebuild everything.
We had the technology.
Well, you don't need too much technology. You just gotta put some fucking Legos back together.
Right.
Yeah, our technology is Legos. Now, I wanted to start off by saying, normally when you design a building, it takes longer than a couple hours. So I cut a lot of corners and I simplified a lot of things.
Cutting corners is tricky because Legos are all corners.
But on what you have going for you, Chris, is that you do have a degree in designing buildings.
I do.
This is true. That's exactly what it says on the diploma. Building designer.
Yeah, so to start out, I wanted to look at what material Legos are made of, and they are made of ABS, which is short for...
Abs.
Abs. That's not short for abs, it just is abs.
It's actually long for abs.
Yeah.
Sorry, I couldn't resist.
It's acrylonitrile butadiene styrene. It's just a type of plastic.
Right.
And I found a bunch of properties on this type of plastic, like the different types of strength, like tensile strength, compressive strength, flexural strength. So I was going to use that. One of the problems with Legos, obviously, is that the weak point would be at where they like interlock, because they're just going to like snap off, right?
Mm-hmm.
And that's where glue comes in. I was thinking of using glue just to keep them together. But I actually looked into it, and apparently at like Legoland and all those places, they don't use glue. They use a solvent called MEK, short for methyl ethyl ketone. And this basically just loosens the surface molecules of the plastic and effectively like welds the pieces together.
Oh.
See, that's cheating. Glue is fine. That's fucking cheating.
I don't know. They use it at Legoland, so I'm going to use it. So basically, if you put two pieces together, I'm going to say it's effectively one piece. And that you don't have that break anymore where they connect.
Yep. Mm-hmm.
So to start off, designing a building, there are different types of loads that you usually look at. It's dead load, live load, wind load, snow loads, earthquake loads. I ignored some of them. I really only wanted to look at like gravity loads just to simplify it. So dead load and live load. Dead load is like all the permanent loads. So in our case, it would probably just be the self weight of the building. And then live loads would be like the people walking around in the building, all the furniture and stuff like that.
Ben falling from the third floor.
Yeah. Exactly, yeah.
So those are the loads we're looking at. I also used load factors. Now, I got my load factors from a building code, but I forget which building code it was. I didn't write it down when I found it. But
it's in there.
Yeah, it's in there.
IBC, International Building Code, is probably where it's from.
So I got 1.2 for the dead load and 1.6 for the live load. So those are the factors I used.
So and those for non-engineers are numbers you multiply your loads by. So if you have 100 pounds, you say 120 pounds because we actually don't know what the fuck we're doing. It's literally the reason we do that.
So to start off, I wanted to just start off with the floor because that's pretty simple. So I was looking at a 50 by 50 foot house. I just wanted to make like a really simple house. So 50 foot by 50 foot, 10 feet high ceilings. And it's basically just one room. So it's just like a cube. So for a 50 foot by 50 foot, the floor would have to be... So for the floor, it would be flat, but you want them to interlock. So it would have to be 2 layers so that they can interlock, right?
Yeah.
You don't want them just like sitting next to each other. So the floor would be 2 layers, and that would be 1.9 million bricks. That's assuming... So for this whole thing, I was using 2x2, like the standard 2x2 brick. You could probably use other bricks, but I just wanted to use all the same brick just for simplicity's sake. So that's our floor. Now to add the walls. For the walls, I just had one brick thickness of wall to start out with, and we can change it if we need to. But the walls would have to be 964 bricks long and 317 bricks high. So each wall would be 1.2 million bricks.
That would be an expensive wall because I know on average for like current modern Legos, like it's about 10 cents per brick.
Yeah.
If you buy like a set. So if you bought the wall set, it would just be like $100,000.
Jesus.
I mean, if you're buying in bulk, maybe discounts. I don't know.
Yeah, maybe discount to like $60,000.
Yeah.
So if we have our 4 walls, we want to add our roof slab. And the roof slab would be the same as the floor, just be a flat thing. So it'd be 1.9 million. But the difference is it's it's not supported by ground. So you need to make sure it can support itself. So, well, analyzing the roof slab, I looked at it as, in engineering terms, I looked at it as a simple span.
Yep.
I don't think it's actually a simple span, but just for simplicity's sake, again.
It acts mostly like one, I think. Keep going.
With the 50 by 50 foot roof slab, I found that the maximum flexural stress of the roof slab is 14,000 psi. And I found that the strength of ABS plastic is 10,000 psi. So we need a column somewhere to support it. So I added a column to the middle. And with the column in the middle, it reduces the stress to 3,600 psi. So that's way lower than our strength, which is good. So we really only need one column.
That is much less than I expected.
Yeah, that's way less.
That's only the weight of the roof.
Oh, true. Yeah.
If we say add, I don't know, a little bit of snow or
anything,
a small bird.
And then next I looked at the column to see if how big the column needed to be. I actually found an article that said a standard 2x2 brick can support 950 pounds before it starts to deform in compression. So I converted that to a compressive strength and found that the compressive strength is 2,400 psi. And the weight of the roof on the column is 434 pounds. So distributed over the area of the column, it would be 1,100 psi. So we actually only need a column that's one brick in dimension. It'd be super thin column.
I'm starting to become doubtful of this math now.
I mean, it's very possible that I made a mistake somewhere. Again, I did this in 2 hours.
I'm a little dubious myself, despite having no civil engineering background.
I am dubious on the fact that wooden columns are a little bit thicker than that.
Well, wooden columns are designed to hold more than just the self-weight of plastic.
That's a good point.
I guess that's true. We can make a very pretty Lego building that no one would be able to allowed to go into.
Yeah.
Or like breathe on.
Yeah, so now we have a floor, we have walls, we have a roof that holds together. Next thing that most buildings usually have is a foundation to hold it all. So I wanted to figure out how much this whole thing weighs. So the entire building without a foundation has 4.9 million bricks. And I found out that each 2x2 brick weighs 0.0025 pounds. So the entire building will weigh 14,000 pounds. Now, distributed over the 50-foot by 50-foot floor, that gives us a bearing pressure on the soil of 5.9 psf.
That's not a lot.
But yeah, that's very low. Just to give some context to that, the average bearing capacity of like a clay or silty clay, sandy silt, which is like on the lower spectrum of soil, that has a capacity of like 2,000 psf. So we're nowhere close to that.
Yeah, we could put like 1,000 buildings on top of each other.
Yeah,
1,000 Lego buildings.
Right. We just don't need a foundation. Yeah, so that's the building just supporting its own weight. But we want an actual functional building. We want to support live loads. So from that code that I got, I found the uniform live load uses 40 psf, like a distributed live load. It's like I don't know how you describe it. Just a uniform load over the entire floor, I guess, downward.
Yeah, like an average, what you should expect on average for stuff moving around in a typical building.
Yeah, that's what the code uses. Obviously, our floor right now doesn't support that, but there are a few ways we can try to fix that. We can add more columns. We can add beams, maybe. What I chose to do is just increase the thickness of the slab. And if we want to support this, then the slab needs to be 137 bricks thick.
There we go. There's the Lego map I know and love.
That's the one.
Which actually, it's only like 4.3 feet thick. It's not that thick, actually.
That's pretty thick.
It's still pretty thick.
Yeah, I was remembering, Ben, I think you had said that beam they were trying to make in the show supported, 11 kilograms before it broke?
The closed end one was 16. And they made a double thick one that was like 40, I wrote that down somewhere, 43 kilograms.
And how many bricks do you think that was, like, deep?
It wasn't that big, actually. It was
like a foot and a half. It was like regular beam sized.
Yeah.
But yeah, 40 kilograms doth not a person weigh.
Right.
So obviously this is a really thick slab, roof slab. And it can work. It will support it. But it will add some weight to the column as well as the uniform loads to the column. So we need to increase the thickness of our column too. So instead of just 1 brick thick and wide, it needs to be 6 bricks thick and wide, which is still surprisingly kind of small, right?
Yeah.
The same for the walls too. The walls need to be 6 bricks thick.
That's a tongue twister, huh?
6 bricks thick. And then this would work. This would support someone standing on it, I think. I mean, I don't know for sure, but
Stamp it.
Yeah.
Stamp it, Chris. Stamp it and build it. Ship it off.
And then just for the foundation thing, I wanted to check to see, because we added some weight, do we need a foundation? And turns out, no, we still don't need a foundation because the bearing pressure is only 146 PSF. So with that bearing pressure, we would be able to build up to 13 stories without a foundation. So you just basically just copy and paste each floor 13 times and it would still work.
There we go. I don't know why we're not building buildings like this right now. Sounds super easy.
Yeah, I know.
Just make them out of plastic.
The thing is, my assumption, because I said that all the pieces were all welded together and that it basically acts as just like a solid piece of plastic, but Legos have empty space in them, so it probably wouldn't really work. There's a lot of empty space in interlocked Legos, but I didn't really know how to account for that, so I didn't.